So now let's see a couple of applications, or maybe you could say examples, of inclusion-exclusion. So first, counting primes. As in the sieve of Eratosthenes. Oh, a little better. All right. So, for example, how many primes less than or equal to 100? Well, x, some number up to 100, is prime exactly 1. So what was the sieve of Eratosthenes telling us? It was telling us that we just need to eliminate all the multiples of primes up to square root of n. So the primes up to square root of 100 are 2, 3, 5, and 7. And so to say that x is prime is the same as saying that x is not divisible by 2, or 3, or 5, or 7. Because these are the primes that are less than or equal to square root 100. Excuse me. So the idea as we'll see generally with applications of inclusion-exclusion, is that often there are situations where it's easier to count intersections than it is to count unions, or maybe in this example, it's easier to count the complement of something than to count the thing. So what does that mean in this case? In this case, the idea is that it's easier to count the number of numbers that are divisible. Let me rewrite that. That are divisible by a certain thing, than to count the number that is not divisible by a certain thing. Or maybe a better way to say it is that counting numbers divisible by a prime is basically the same as counting numbers that are not divisible by that prime. But counting numbers that are divisible by more than one prime is quite easier than counting numbers that are not divisible by some collection of primes. So that is why we are using inclusion-exclusion, because the multiple intersections are much easier to count than the multiple unions. So let S sub p equal the numbers 1 to 100, whoops, 1 to 100 that are divisible by p. So we're doing this for p is 2, 3, 5, and 7. Then primes less than or equal to 100, so besides the ones that we're choosing out, cardinality of this set, let me just put some big cardinality bars on it, is equal to the cardinality of S2, which is the numbers that are divisible by 2, complement, so the numbers that are not divisible by 2, intersect S3 complement, so now this is the numbers that are not divisible by 2 nor by 3, intersect S5 complement, intersect S7 complement. So this is the set of numbers that we're looking at, and the number of them is the number of primes up to 100, besides our 4 guys that we're leaving out. So by good old De Morgan's laws, this intersection of complements is the complement of the union. So S2, union S3, union S5, union S7, complement of this whole thing. Get a better complement bar, there we go. And by our complement rules, this is equal to the size of the total set. So we're taking complements inside the set of numbers 1 to 100. So it's 100 minus cardinality of S2 union S3 union S5 union S7. And this thing, again, is a little bit difficult to count, but fortunately, we have good old inclusion-exclusion to tell us what this is. So it is 100 minus cardinality of S2 minus cardinality of S3, again S5, again S7, plus the cardinality of S2 intersect S3, plus the cardinality of S2 intersect S5. And let me not keep writing out all of these things, but so on all the double intersections. Then minus S2 intersect S3 intersect S5, minus all of the triple intersections, and finally plus the single quadruple intersection S2 intersect S3 intersect S5 intersect S7. And the point of doing all this manipulation and writing it out this way is that it is easy to count excuse me. For example, the cardinality of S2 intersect S3 intersect S5, what is this? Well, being divisible by 2 and 3 and 5 is the same as being divisible by 2 times 3 times 5. And the number of numbers up to 100 that are divisible by that thing is equal to 100 divided by that thing, and then take the floor, which, if you will recall, means round down to the nearest integer. So this is, if this is not immediately obvious to you, just think of some examples. How many numbers up to 100 are divisible by 2? Well, that's the evens, and it's every other one of them. So it's 100 over 2. How many are divisible by 4? It's every fourth one, so 100 over 4. And the floor is just because you're going to get an integer number, and it's going to be the floor because if you get a fraction, that means you haven't quite gotten to the next multiple yet. So, putting this in for all of our things, the number we are looking for is 100 minus 100 over 2 floor, minus 100 over 3 floor, minus 100 over 5 floor, minus 100 over 7 floor, plus 100 over 2 times 3 floor, and all of the double intersections, minus 100 over 2 times 3 times 5 floor, minus triple intersections, plus quadruple intersection, 2 times 3 times 5 times 7. And these are things that we can just compute pretty much even off the top of your head. But let me not do that all longhand. Let me just say that this is equal to 21 when you add it all up. Let's compute this one real quick, why not? What is 2 times 3 times 5? It is, so that's 15, times 2 is 30, So 100 over 30 is going to be 3 point something, because 30 times 3 is 90, and 30 times 4 is 120. So the floor of 100 over 30 is going to be 3. So this term is a 3, and if we compute them all out and collect them all up, we get 21. So that is telling us the number of primes less than 100, or to be precise, the number of primes is actually 21 plus 4, because in this count we left out 2 and 3 and 5 and 7, because those are the primes that we were using to count in the first place. So there are 25 total. Very good. So let's take a look at another application, another example of inclusion-exclusion. How many surjective functions from a set A to a set B, where this guy has, let me match my letters to my notes, this has m elements, and this has n elements. So of course, m should be bigger or equal to n. Oh geez, that's the opposite of what I wrote, but I think it's right. Yeah, m should be bigger if we're going to have surjective functions. So how many surjective functions from A to B? We saw before that we can count the number of injective functions. That was basically just taking, that was a much simpler counting problem. It should end up just being some kind of, some kind of product rule that we were talking about before. But how many surjective functions is quite a bit more difficult. But now that we have inclusion-exclusion, we can do it. So let's do it. The idea, again, in this case, why are we going to approach it from this direction? The idea is that it's easier to count. How many functions miss some particular elements? So it's going to be a very similar flavor to the example that we just did, where we are taking some cardinalities of complements of the thing we're trying to count, and sort of doing this counting from both sides technique. So, whoops, let B equal, we just want to name these elements so that we can refer to them. B1 through Bn. And define a set S sub I to be the set of functions from A to B, such that Bi, so this I is corresponding to one of these Bi's. So functions such that Bi is not in the range, or rather the image. So by similar reasoning to what we used above, the number of surjective functions is going to be equal to the total number of functions minus the cardinality of S1 union dot 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 union Sn. Basically because S sub I is the functions that do not have that thing in the image. So the union of all these sets is the functions that are not surjective. So the functions that are surjective is just the complement, and we count it like this. So first of all, what is the number of functions from A to B if A has m elements and B has n elements? Well, by the product rule, we have m slots and n choices for each. So that is n to the m. I believe, at least that's what it says in my notes. Hopefully that's correct. And then minus, so by inclusion-exclusion, minus the sum, 1 less than or equal to I, less than or equal to n, cardinality Si, plus sum 1 less than or equal to I less than j up to n, Si intersect Sj, etc., plus minus 1 to the n, S1 intersects all the way through Sn. Now, we said it was going to be easier to count these sets Si and their intersections. So let's do that. Hopefully we were right. Now, cardinality of Si1 intersect SIR. So this is just any R intersection, meaning an intersection of R of our sets. This is just equal to the set of functions from a set of, what was A? I'm going to keep forgetting. A was M. So we can think of this as being functions with the same domain, but we are just shrinking the codomain so that it does not include those elements in the image. So it's functions from a set of M elements to a set of N minus R elements. And again, by our product rule, the number of these is N minus R to the M. So let's zoom back in here. And so each of these intersections has that cardinality. In particular, for a fixed R, they are all the same. And the number of terms in one of these sums, as we were saying before, and I believe when we proved inclusion-exclusion, the number of terms is just n choose R. So this is the number of R intersections in the sum. So the total count we get by plugging this in for each of these intersections and plugging this in for the number of terms in the sum. That means they just get multiplied together. So the number of surjections is equal to n to the m minus n choose 1, n minus 1 to the m, plus n choose 2, n minus 2 to the m, all the way down to -1 to the n minus 1, and choose n minus 1, 1 to the m. So here we have an explicit formula for the number of surjections between two sets. So here are some examples of inclusion-exclusion, and you can see that they are a little bit involved and take, certainly they do take a bit of computation and a bit of work. But it's worth noting that also, for example, in the case of these counting number of surjections, it does allow us to handle some more difficult counting problems than we were able to before.